So on to the next step here, we have our compression step. And so with our compression step, we have the initialization of working variables, the computation of temporary words and mutation of working variables, and then integrating the computed and mutated working variables with the initial values passed into the compression function. So let's get started. Okay, so before we jump to the code, I've just pulled up the RIPEMD-160 specification again so we can have a look at the pseudocode. And so what's happening here is we have our initial values, obviously, that we initialize our registers with, but we're going to have two sets of registers. So we have A to E, and then we have A prime to E prime, and we are initializing both sets of registers with the same values. And then once they're initialized, we're going into this loop, and it's an 80 round loop, and what's happening is you'll see that these two steps are corresponding to these first registers, these first set, and then these two steps are corresponding to the set of prime registers. And so what we're doing here is we are adding, and I should just point out that this is not an XOR, it's actually an addition. A little bit confusing there, but that's how they wrote it. So what we're doing with this step is we are adding these values together, and once those values are added together, they're being rotated left by a certain amount. So this X value is referring to which word in the schedule is supposed to be done in this step, and that's actually provided right here. So this is the selection of the message word. And so basically what this is doing is it's this RJ value is pulling in an index based on this each row. And so you can think of this as going like 16 times, and then another 16 times, then another 16 times, and then another 16 times for 5 rounds of 16 in total, where this is happening for both the A to E and then A prime to E prime. And so once we have this inner amount, again, we do the rotation to the left, and then once we do the rotation to the left, we add the E value. And then once that's done, we do the mutation. So we go E gets assigned to A, D gets assigned to E, rotation or rollover to the left by 10 of C then gets assigned to D, B gets assigned to C, and then the temporary word that we just calculated in the previous step gets assigned to B. And so we go through this, it's a total of 80 rounds, and then after that is all done, then we do this final step where we go H1, so that was our initial value here, added to C, added to D prime becomes our T value, and then H2 added to D added to E prime becomes our H1, etc., etc., and then T becomes our H0. And that is the values of our chaining variables. And then just like SHA-256, if there is more than one 512-bit message block, these values would be passed as the starting values to the next round. And it's definitely a little bit confusing to look at first time, especially if you don't have a computer science or a math background, but hopefully it'll become more clear once we go through it with the code. Jumping into the code, so here we have our initial values, and those are being passed in. I'm just with that step here. So it's this line right here. We're taking those values in, and then we are passing those to our compression function with our message schedule. And so our first step is to just initialize our working variables. So we have A to E here, and then A prime to E prime. Those are initialized with the same initial values that were passed in. Once we do that, we initialize our temper prime. Those are just set to 0 for now. And then we get into our 80 rounds. So the first 16 rounds, I didn't set up a separate logical functions file for this one just because the message schedule construction doesn't require them, so everything can be done just inside of this compression function. And so instead of, like, if I'll just pull the pseudocode back up for a second, instead of including this all in one step, I've split it out into two. And so the first thing we're doing here is we're taking A, we're adding that to B, which is XORed with C, which is XORed with D, and then that, because that's the function, the first function, because I'll just pull that up and show you where that's coming from. So we scroll up, it's this first function here. So x is XORed with y, XORed with z. And then we're adding our first message schedule word. And so this word I is just referring to these. So it's this first row is what we're dealing with for the first 16. And then same thing with our rotations, and then obviously the same thing with our word prime, etc. I'll just jump back down here. So we're basically giving our message schedule, which we fed into this function at the start. So this is our schedule of 16 words, and we want to feed the right words in. And so we do that by getting the index value from this array of values here. And then once we have that, we add our constant value, and I'll just quickly show you where that's coming from. I think you just saw it, but here are our constant values that are specified, and you'll see that it corresponds to this round of 16. So we have our constant value 0 is the first one. And so we add that, and then once we have that, we do our bit rotation to the left, and we figure out how many times we want to rotate it to the left based on that specified schedule. So this is the first one that we're doing. So the first time this is going through this, it's going to be 11. And then once we have that, we add E to it. And then we have our temporary word. And once we have our temporary word, then we're following this sequence here. A becomes E, E becomes D, etc. That's this step right here. And so we do that 16 times for the A to E registers, and then we do something a little bit different for the prime step. And so I'll just pull the specification back up one more time. So for A to E, we're going to be doing it in this order. These logical functions are done in this order, just the regular order. And then for the primes, they're actually done in reverse order. So if we have a look at this function here, that's what's happening. So we have B being XORed with C or not D. And then again, we have our message schedule. The word from our message schedule that is needed is coming from this row right here. So the first one is 5. And then we have our constant value. And our constant value that's being used is, again, specified here. It's these bottom prime values. So the first one is this 50A 28E BE6, sorry. And the process is pretty similar. So we're getting our temp word here, and then we're taking that and we're rotating it by the specified amount. So that is going to correspond to this row here. So that's number 8. And then being added with E prime. And then when that's all done, another kind of similar process here. We have our variables being reassigned or being mutated around. And we have another little rotation happening here, but it's pretty similar in that respect. This step is pretty much the same between the two. And so we go through each of these rounds essentially. So there's 5 rounds of 16, and I've set it up this way, 0 to 16 and then 16 to 32, because it makes the rows, you can use a single array that way. So this is just one array, and then you have the first 16, 0 to 16, or 0 to 15 I should say, and then 16 to 32, etc., etc. And you go through each of those rounds for A to E and then A prime to E prime all the way down to round number 5 here. And then just like in the specification, once all 80 of those rounds are complete, that is when we do this final step. And so the final step is right here, and that's the temp value comes from H1. And so if we just jump back up, we can have a look at where H1 is coming from. So that's this step right here. H1 is coming from these chaining values, our initial values. Let's just jump back down here. And so we have H1 being added to C, and then that's being added to D prime. And then H1 becomes, that was our temp value, and then H1 becomes H2 plus D plus E prime. Then H2 is H3 plus E plus A prime. And you'll see how these values aren't being written to until they're being used in the previous step, until the final value, our first H0 value, becomes our temp value. And then we have our H1, our H0 to H4, our 5 values, and we assign our chaining values, or those to our chaining values, our array of values, and then we pass our chaining values back to our main function here. And then again, if there were any more 512-bit message blocks that needed to be compressed, they would go through this loop again. But using our input of ABC, we only have the one message block, so this is only going to be done one time. And that more or less covers the compression function. It is pretty complicated, but it's also a lot of fun. It's really nice to look at because it's kind of an elegant way to do things. But we'll cover the final value construction and output in the next video.